Thank you very much. Yeah, so I will talk about multi-magnon Floquet topological edge states. And this is work that I'm doing with Bill, but I'm also supervised by Tami Perebarnea at McGill University. So I want to divide this talk into small parts. One is some background. I know a lot of you are already experts in this. But I want to talk about topological matter, multi-magnon topological states, and also Floquean topology. And just after that, go into our project. So the topology in condensed matter, the role of topology in condensed matter came in 1980 with the discovery of the quantum Hall effect. So it was discovered that when you have a two-dimensional electron gas and you apply the magnetic field in the z direction, you have your Hall resistance quantized. And this quantization is related to a topological invariant that is known as the Chern number. We have seen this topological invariant appear in some talks. And it's just every energy band has a Chern number associated with it. And it's just given by the sum over the Brillouin zone of the Berry curvature. So the Chern numbers are very robust, and the reason why they are very robust is because they cannot change unless you close your energy gaps. So in that sense, their properties are very robust. And what is interesting is that the Chern number can differentiate between two different phases. So when the Chern number of your bands is 0, you will say that you are in the trivial phase. But when they are not 0, you are in the topological phase. And the topological phase is characterized for having these chiral edge modes that are ultimately responsible for this quantization of the conductance. So here is a two-dimensional electron gas. We are talking about electronic systems. It all started here, but there are also topological magnons. So here, for example, we have a ferromagnet, and here is just a schematic of these edge modes that also appear in magnetic systems. And instead of having electrical conductivity being quantized, what we have is thermal conductivity. And the reason is electrons have a charge, but magnons, they don't have a charge. So we cannot really look at the electrical conductivity. However, a signature is the thermal Hall conductivity, and this is because magnons do carry some energy. So if you apply a thermal gradient in one direction, you get some energy current in the transverse direction. And this current is also transported by some edge states. And these edge states, I think are very... So it's not, what's not interesting with magnons is probably the quantization of your observables, but more just the presence of edge states. So we have seen in talks, especially at the beginning of the week, that non-reciprocity is desirable characteristics of magnons. So these chiral states are clearly only moving in one direction. And just to connect a little bit to what Michael was discussing yesterday, the use of these edge states, topological edge states, have also been proposed to entangle spin qubits. So some of the earlier work on topological magnons was motivated by the discovery of the thermal Hall effect in lutetium vanadium oxide. And this material is composed by alternating layers of Kagome and triangular lattices. So here I'm showing just the Kagome lattice. If we focus on this lattice and try to see what's going on, we can describe it by a Hamiltonian that has some exchange, Heisenberg exchange term, some Dielonchinski-Moriah interaction, and a magnetic field. So this Kagome lattice has 3 atoms per unit cell, and that results in 3 energy bands. So the bulk energy bands are in gray here, and these black lines are the edge states that appear due to the non-trivial topology of the system. And the non-trivial topology here arises because of this term, the Dielonchinski-Moriah interaction. And one way to think about it is that, well, here this material is ferromagnetic, And the DMI, well, so the excitations are single spin flips at each side, well, magnons, as we have seen. But what the important thing is that the DMI, when you have a spin flip going from one lattice side to another, it moves and it gains a phase. And this phase is analogous to the phase that electrons gains when you have a magnetic field in this 2D electron gas. And so it's analogous to this magnetic field that breaks time reversal in the electronic system. So in some sense, the DMI is breaking an effective time reversal symmetry in the magnetic system. It's not a real time reversal symmetry. Of course, since we have magnetic order, we will not have time reversal, but it's an effective time reversal symmetry. And we can make this analogy between the magnetic field in the electronic system and the DMI in the magnetic system. So here we are just talking about single magnon states, but we can also have topology in the two magnon bands. We can write a two magnon state in this way. This is not an eigenstate of our systems, as Silvia was telling us yesterday. However, they can be a useful basis in some cases. So, for example, Keane and collaborators were looking at this Hamiltonian that is essentially a generalized XZ Hamiltonian, with some transverse coupling J perp and some longitudinal coupling J set. And what plays the role of the DMI is that you have this phase that is hopping, that you gain as the spin flips hop from one lattice side to another. But what is interesting is that if the anisotropy is very large, so if this J set is much larger than this J perp, you have as playing in energy between states that have two spin flips together and states that have two spin flips far away from each other. So this we call the two magnon continuum, and this we call the two magnon bound states. So all of these states are superpositions of delocalized adjacent spin flips, and this is just because this happens when the J set is much larger than J perp. And we can focus on this lower energy subspace and try to see if there are some topological excitations in this subspace. So, for example, for this Hamiltonian, you can look at the spectrum with periodic boundary conditions. You can compute the Chern numbers, and if they are non-zero, when you consider Riemann geometry, as the one shown here, you can have edge states that are localized. For example, this edge state is localized to the bottom of the sample, so it's this one, and it's moving in the right direction. And the other edge state is at the top of the sample and is moving to the left. And so here we have these chiral edge states, but these are two magnon excitations. So it was also proposed that you can have a mixture of single magnon and two magnon states, and then being topological. And here I'm using the term hybrid, but it has nothing to do with hybridizing different excitations. We have seen a lot of photon magnons, magnons, but here I'm just referring to the fact that the topological excitations are made of single magnon states and two magnon bound states. So when you have this anisotropy, the two magnon bound states is separated from the two magnon continuum, as we saw earlier. And in some cases, you can have these two magnon bound states cross the single magnon energy band. And this, for example, in the work done by Mook and collaborators, happens when you have beyond nearest neighbors interactions. And if you have a DMI in your system, these two bands hybridize, and there's a gap opening. And the DMI also gives this phase to the spin flips as they hop. So the bands can be topologically non-trivial and have these edge modes connecting the bulk bands. Okay, so now I'm going to just talk a little bit about the ideas of Floquet in topological matter. And so Floquet systems are basically systems that are described by a Hamiltonian that is periodic in time. And the way that we can look at the topology of these systems is by analyzing the Floquet Hamiltonian. And the Floquet Hamiltonian is just related to the time evolution operator of our system over one period. And then we can apply all of the topological, or we can use the topological classification schemes that are used in static systems for this Floquet Hamiltonian, which is static. It doesn't depend on time. And then we can compute the eigenstates and the energies or quasi-energies, as they are known, of this Floquet Hamiltonian. And we can compute our Chern number, our Berry curvature, and then the Chern number. And for example, there are different kinds of driving. So you can have a, so your Hamiltonian is periodic. So you are driving, is basically you are driving your Hamiltonian with some frequency. And if we focus on the case of resonant frequency, that means that there are some energy in your bands that are resonantly coupled. One way to think about it is, okay, so you have these initial two bands. These vectors, they describe the Berry curvature in momentum. And when you do apply this resonant drive, one way to think about it is anything that is inside this circle, this resonant circle, is exchanged with this, with everything that is inside this circle. So if you go to a rotating frame, you will see that this band will move here, and then after the hybridization, it's just as if these two regions are swapped. And what that means is that you can swap Berry curvature from one band to another. And that results in you changing the Chern numbers of your bands. So you can start with a trivial system that originally has 0 Chern numbers, and by effect of this driving, you can modify the Chern numbers of your bands so that they are non-zero, and you can have the presence of these topological edge states. Okay, so now with this background given, I'm gonna go into what we are doing. So our idea is that we want to generate some edge states in a spin system that is composed by single and two-magnon bound states, similar to the work done by Mook and collaborators. But here, we want to do it by driving the Djalon-Chinsky-Moravia interaction. So the goal is that in some systems, having a static DMI, as in the case of the work done by Mook, it's not enough to have topological edge states. But if we drive this DMI, we can manage and generate these states. So this is the model that we consider. It's a two-dimensional square lattice. It's very simple. And our Hamiltonian is is a time-dependent Hamiltonian, and it has a static component and a time-dependent component. And the static component is just an XXZ Hamiltonian, so it has some longitudinal coupling, JZ, and some transverse coupling, JPerp. And there's also a Zeeman term coming from a magnetic field. And then we have these Djalon-Chinsky-Moravia interactions whose amplitude will be time dependent. Here we are thinking in a scenario that you can do this with an electric field or by applying some strain to your system. And this is the regime of consideration that we work on. So we work on the regime where the longitudinal coupling is the largest energy scale, followed by the transverse, and then the energies associated with the EMI. So let's look first at the static Hamiltonian, the XXZ Hamiltonian. So it has a ferromagnetic ground state, and then it will have single magnon excitations, and then two magnon bound state excitations, and then the two magnon continuum, and then followed by three magnons, and so on. And so what allows us to have these two magnon bound states separated from the continuum, as I mentioned previously, is just the high anisotropy. And the idea is that we want to drive the DMI. The DMI will, it does not conserve the number of spin flips or magnons, so it will couple these bands with the single magnon band with the two magnon bound states band. And it will couple resonantly if you choose the frequency to be given by the energy difference. However, you also need to worry about the coupling of the 2-magnon bound states with the 3-magnon spectrum, because it will also, just as we can connect these two by a non-conserving, or by an interaction that does not conserve the number of magnons, we are also going to try to connect, to couple the 2-magnon states with the 3-magnon state. But as long as the DMI is weaker than the transverse coupling, we're going to have some detuning here. And if the ratio between the DMI and this detuning is small enough, we can neglect this coupling. And so this strategy complements the previous work that I was mentioning earlier, where the crossing of the single magnon band with the 2-magnon bound states bands occurs by the presence of some next nearest neighbors or beyond nearest neighbors interactions. So this is another strategy to get these edge states. So if we just look at the XXZ Hamiltonian, it's topologically trivial. It's not very complicated to see why. The reason is that, okay, we can look at these terms. So the longitudinal coupling and the Zeeman term only tells you about the energy of different configurations of spin flips. And the transverse coupling is just a hopping term for spin flips. But when a spin flip hops from either to the right or to the left, there's no phase associated with it. So there's no breaking of this effective time reversal symmetry. And we do not expect to have a non-zero Chern number. However, to see how the DMI breaks this effective time reversal symmetry, here I should have an effective. But one way to think about it is, okay, let's think about our low energy subspace given by single spin flips or two spin flips that are adjacent. So one at R and another one at the X neighbors or at the Y neighbor. We can put these three low energy states in a lattice in real space. And the DMI, which does not conserve the number of spin flips, will couple these states, but it will give them a phase as they hop from the single spin flip to the two adjacent spin flips. And so you have these little loops in which you are gaining a phase, which again is analogous to the phase that electrons gain as you apply a magnetic field in a 2D electron gas. So if the DMI breaks time reversal symmetry, why this is not enough to have edge states in some cases? So for example, in our case where we don't have beyond nearest neighbors interactions, what happens is that the topological bands, meaning that they have non-zero Chern numbers, they overlap in energy. So the maximum of the lower band is above the minimum of the upper band. And this, when this happens, you cannot guarantee that you will have edge states, even though your Chern numbers are non-zero. So so with just static DMI, you will not have topological edge states. So the strategy that we are proposing is, okay, in these cases, you can drive the DMI to connect this single magnon band to the 2-magnon bound states band, and you can produce a band inversion in this point in momentum space to have an actual energy gap between this lower band and the two bands above. And by doing this band inversion, you are changing the Chern numbers, so you are going through a topological phase transition. And this, the presence of this global gap, energy gap, will allow you to have some edge states in this in the driven case. And that's in fact what we do if we impose open boundary conditions. Here in this case, in the Y direction, and we still have periodic boundary conditions in the X direction. So if we go ahead and compute the spectrum, we see the first band and the middle band, they are connected by these edge states. And if we plot these edge states, we see that they are localized to the lower or the upper edge. And we have this chirality that is characteristic from from the topological edge states. And furthermore, we can try to tune these edge modes. So if we imagine a situation where the DMI can be independently controlled between X and Y neighbors, we can think of a situation, for example, where they have the same time dependence, but there's a relative phase between them. And this relative phase can control the chirality of the edge mode. So here, for example, we're plotting the Chern numbers of the three bands as a function of this phase. And we can see that there's a phase transition where the first and third band exchange Chern numbers. And what that means is that the chirality of the edge mode, so here is going in the counterclockwise, it changes to a counterclockwise direction. So by independently modulating these DMIs, you could control the chirality of your edge states in your system. So yeah, so this is this is essentially the project. So just to reinstate the main points. The idea is that you can drive the DMI to produce topological edge states in systems where in static DMI you wouldn't have these edge modes. And if you control the parameters of this drive, you can control the chirality of your edge state. So it can be, you can change from anti-clockwise to counterclockwise. Yeah, and if you have any questions, I'll be happy to discuss.
Right. Thank you, Ivan. We have plenty of time for questions. Let me run there.
Thank you for this nice talk. Can we take it a bit from the beginning where you showed the magnon band? Yeah, like a bit further forward. Forward.
Forward.
Forward. Yeah, forward. So here, yeah. So can there be a case where you have a non-trivial Chern number for a two-magnon bound state, right?
Yes.
Of magnons consisted of bands that have trivial?
That have
so like single magnon is trivial, but the two magnon is non-trivial. Can
Yes.
there be a case like that?
Yeah, you can have that case. And yeah, I mean, for example, if you only have, in our case, if you only have DMI, that's actually what happens. So maybe I can show this picture. So in this case, the single magnon band is trivial, but these two, the magnon bound states band are non-trivial. Here, however, we have the problem that since the bands are overlapping in energy, you will not have the edge modes. But yeah, it's totally possible to have this situation.
So in the figure before, where we can see the two magnon continuum as well. Yeah. So the fact that the two magnon bound states branch below the two magnon continuum has to do with the sign of the anisotropy?
Not the sign, as long as you have an anisotropy, an Ising anisotropy, these will be separated. And you can think about, the Ising limit. Two spin flips that will be far away from each other will basically have this energy. And two adjacent spin will have this energy. And as you start increasing the hopping, there's going to be the bandwidth of the two magnon bound states are going to be is going to increase. But it doesn't matter if it's it doesn't matter about the relative sign to have the bound states.
To have them, yeah, but they could branch above the magnon, so it would cost more energy.
Oh,
to
yeah,
bound
okay.
them.
So yeah, so if you have a complete antiferromagnet, yeah, the two magnon bound states will be above. That's what you mean?
Yes.
Yeah.
And is there a realistic material for this model?
So we don't have a very, like with the name, a candidate material, but we have seen that, in Janus monolayers, for example, you can have this Ising anisotropy, and you can have also DMI.
Right.
some van der Waals materials might have you might have these same anisotropies, but one material we don't have a particular material in mind.
And the frequency at which you drive with the DMI plays any role? I'm not sure if you mentioned that.
Yeah, so the frequency needs to
Match the gun.
yeah, to match this energy difference. So it has to be of the order of the exchange interaction.
Okay. I'll leave some room for more.
Thank you. Thank you. We have more questions here.
Hi. I guess it's a little bit of a more general question. So I know also we always work with topological magnons, and okay, we use this bulk edge correspondence, but as far as I know, this bulk edge correspondence has been proven for fermionic systems. Is this correct? And is this generally valid for bosonic systems? Or is this something that we just use but has not been rigorously proved? And yeah, so you can't say you don't know. It's just I'm
Okay.
wondering if you know.
Yeah, I mean, it hasn't been proven in the sense that they haven't seen an experimentally the single.
No, I'm so forget about experiments. So I'm
Okay.
probing the edge states is it's another matter. But I'm asking about the bulk edge correspondence. Can we rely on this, or do we have to, for each system, solve the system in a finite geometry and look if there are edge states?
Yeah,
This is my question.
Yeah, at least the way I think about it is case by case, as you say. I haven't seen, I don't know, I don't think there is a proof, but it's, yeah, so you have for every system, you define your topological invariant, right? And then you can put two together and you can just show that you will have these edge states. But is that what you mean? Like?
So what do you mean you put these two together?
So you have, you have a Hamiltonian and then a Hamiltonian that is periodic, but then you just write it for a finite length. And you put two regions, one in which the system is trivial and one it's non-trivial. And then you compute you find the solutions for the edge states.
Okay, so you do it explicitly,
Exactly.
and
Case
in
by
this
case.
case, this is
Yeah.
also what you did. So
Yes, yeah.
Okay, so
yeah.
you checked explicitly that
Exactly.
these edge states in this basis that you're calculating of the two magnons is there.
Exactly.
Okay, that was my question. Thanks.
Okay.
Okay, we have time. I think Poliana.
I actually have a basic question. What do you mean by calculating the chair number for each band?
Okay, so the chair number so the chair number is so for every band, we have our discrete lattice, and the way we compute it is just we take we diagonalize our system, we find the eigenstates, and then we compute the very curvature for each momentum in the lattice, and then we just sum across the momentum space. So that's how that's what I mean when I say we compute the chair number for each band. So each band will have its own chair number.
But in electronic systems, usually you have the band structure, and then you do the calculation, and then you have a single chair number. Like it's either trivial or not.
Yeah, but I guess maybe it's because if you have two bands, for example, the sum of all the chair numbers in your bands has to be 0. So if you have two bands, you can just talk about one chair number because one band will have 1, but the other one has to be -1. So maybe that's why sometimes we just use one churn number for each band. But in general, each band has to have the churn number. So if you have 3 bands, you can have -1, -2, and then 3, for example. So in that case, we need more than one number to.
Okay, thanks.
Oh, but I think there is someone in line. Okay.
So I guess if you want to see like some signature of this kind of thermal Hall effect with the edge states, you kind of have to know like how the magnon distribution is, right? How the states are populated.
Exactly.
So with now you're driving, you're shearing the system, you're applying pressure, so it's doing work on the system. So have you kind of thought about how the magnon distribution is like when this in this kind of driven state and how the states are populated?
Yeah, actually, that's a good question, and we don't really know because it's, when you have a static case, you can use the Bose distribution, and then you can compute observables. But when you are driving here, it's a little bit more tricky than that. So the short answer is I don't know exactly, but you can think about, or I guess what I think about is you can start driving your sample. And if at the beginning you are in the ferromagnetic ground state, maybe when you are driving, you can just, with a pump pulse, you can just excite one of these states that are now available because you are driving. But yeah, so.
Question before moving to the next speaker. Next.
So I just make sure and I understand things. So this description here is the usual thing people do in BHC model and all that. But now you have an interacting system and you have time dependence. The Floquet stuff, it's also like a block type theorem, but the energy is not conserved. Now what's confusing me a bit is, can you actually prove that all of this is still valid when you have a time dependence, that you actually find edge states, that your chair number is still valid, and also have things like 2 magnons, so everything is like single particle for the usual topological band theory, right? So what is the connection? How do we think about it here?
So you mean, how can we be sure that we can see these topological effects when we are doing this?
Yeah, you're translating something from time independent to time dependent. There are some analogies, of course, because you still have some kind of a brilliance on the Floquet states, right? But this is interacting as well, right?
Yeah, it's interacting.
Everything is done. BHC model, for instance, which is the standard paradigm, is just non-interacting.
Oh, yeah. So it's true that we have interactions here, but if we focus on the low energy subspace, we can actually think about it as a non-interacting system. Because the interactions, what they do is they will take you from a single magnon or single spin flip state to a state with two magnons. But if you focus on this low energy space, where these 3 kind of excitations are separated from 3 magnon excitations, it becomes essentially a non-interacting Hamiltonian. So the interactions in that sense are taken care of, or it's, you can think about it as an effective non-interacting system. And about the driving, it's one way to think about it is, maybe I can show this. Yeah, I don't know if that answers your question. And the driving, there are many ways to think about it. So one way, for example, in many cases when you have resonant driving, you can just go to a rotating frame, and your Hamiltonian will have these char numbers. So you can exactly. So you can at stroboscopic times, it will come back to itself, and then you will have the edge state at stroboscopic times. But you can also see the evolution within the period. And what will happen is you might have a superposition that is localized. So superposition, I mean single magnon and two magnon states, and what age. And the coefficients of that superposition will oscillate with the frequency of your drive, but it will be still localized. So I think we can, I think we can be not too worried about the driving somehow not seeing the topological features in the driven case.
Okay, with that, let's thank Ivan once again. And the next speaker is Jordan from Faculty of Physics, Belém. Thanks, Jordan. Thank you also for all those questions. They make my life easier. Let's skip the energy.